Good morning on March 17th. This is the official observance of St. Patrick's Day, right? Or at least that's what I was hearing on the radio. I don't have the Irish blood in me at all, so I don't feel any need to wear green. You're wearing a green shirt, so you must have some passion for it. So what I want to talk about, nothing is live right now, so I'm not going to try to click any links, but set number 6 did get posted over the weekend. I've endured a lot of different things, mostly working at the house, if you can believe it, working a lot of hours cleaning and packing and trashing and so on. I finished grading set number 3. I've started through the exams, and we're going to talk about the exam today because I want you to see it, and it will be coming back to you soon enough, the way I see it. Right now, I'll just say that the exams I've graded, I'm seeing a high of 89, a low of 41 so far. So, and then I've got one score at 75. So I'm seeing a wide variation, and I don't know what else I'm going to see. I can't predict what I'm going to get to. I've graded parts of more than others to try to get a sense of how things went. I actually think page 1 was probably the hardest page just because it had calculus on it, and it's also been the hardest one to grade too. But we are going to look at the exam so that you can look at that, see that. We're also going to look at a preview of the first project, which I have out there too. So without further ado on any of those subjects, I'm going to jump down here, and first I'll talk a little bit about what this project looks like, because I was messing around with this late last night and then this morning. This is just so you know what's coming, and I've got the first problem all written out. I just have to write the tasks up for it. But it's been assigned before. It was assigned, believe it or not, in real-time DSP, a course I used to teach using embedded systems, microcontrollers, and was implemented in real time. But I think it's going to work here too because it's communications theory based. So the basic layout of it is teams of, this thing's not doing what I wanted it to do. Teams of at most 2, and the theory behind that is working in teams of 2 is good. It's like those of you that are in the lab, which is everybody in here except for one. You look at each other and nothing goes around in a circle. When you have like a senior capstone design team, I always observe that if you had 3 and 4 people, the buck would pass around and things always didn't get done as well as they could have. It's more of a circus act, who's doing what. But teams of 2 is very helpful. I think you can synergize off each other. If you're a graduate student, then you work alone. And you can talk to me about that if need be. If you want to work alone and you're a senior, but I encourage you to work together and you can divvy out the tasks. Right now I looked at the calendar and I said with spring break week next week, I settled on tentatively saying the 7th that it would be due on, but that could change too. I could push that out to Friday if I wanted to. Since I have the calendar open right now, I just want to refresh our memories on what is happening with me traveling. So I leave on the 17th to go to Amsterdam, actually, for the beginning of this river cruise. So my intention is, though, that on the 14th I will be doing a review for exam number 2. It'll be not exactly centered like the past exams have been centered because we didn't have anything from chapter 3 on exam 1, but we'll have a lot of chapter 3, which we're going to wrap up today, and then probably the start of chapter 4 that'll be on the exam of the 21st. And of course, when I post old exams, you'll have old exams for exam 2, and then you'll be able to combine that with what you saw on old exam 1. Does that make sense? I mean, we'll discuss what it will be covering, but you'll have problem solved, things like that, from sample exams. Then on the 28th, there will be, doubtful will be a guest lecture. Dr. Trimboli highly recommended to me I just simply use an old lecture video. If I have the time, I would like to make a new lecture video because I have no idea, worst case scenario is I could say you have to watch 2 lecture videos because one of them, they won't line up properly. And I don't know. I look at anything I did in the past as being in the past, and in the present it's better if I can produce it okay. But I don't know how all that's going to happen. I have a son that's getting married on the 11th, so that's also kind of running interference on things I want to do. But at any rate, this is the description of what the problems will be. They all will have a common theme of needing to use DSP modeling, but not to the extent that I think reaches beyond your understanding. And I will hint and provide examples in a sample notebook. This sample notebook that's referenced right here doesn't exist yet, but it will be a sample notebook that has some framework for all 3 of the project problems. That's how I like to do it. I give you something that you can work in, and then you can author in that too. And if you're splitting the tasks up, you can combine into one project document. So just to make that clear, it always has gotten confused in the past. If you work in a team of 2, you are turning in one project report. It saves me from having to grade extra papers, and I want you to think of it that way. If one person on the team wants to be the editor and final author, the document that gets submitted as a PDF to me, that's fine. There very likely will be the Jupyter Notebook, printed out as a PDF, and also there could be some WAV files where you're processing things and sending them through and demonstrating to me that what you wrote in code does produce an output that you can listen to, let's say. So the first one is going to be, first project, which is already written in this document, is using a DSP, developing a DSP-based receiver that can operate with a single A to D converter and then form an analytic signal, and we'll look at that in a second. The second one is related to a topic we'll look at today, pulse code modulation. It's a very popular scheme. It's basically the backbone of what became the compact disc a long time ago in 1976. And some of you probably still listen to compact discs. Is that true or no? You might download it from iTunes or something and have it on your device. But the compact disc, though, did start with using a format called PCM, and I'll get into that more later. PCM then migrated further down the line to being not precise, bit true type processing from analog to digital, but instead using various lossy or lossless codecs and things. That is the more common streaming means because it saves bandwidth. But it is still the core of converting analog to digital, and it's what an A to D converter basically does too. But what you have to do whenever you send bits, whether it be PCM or some other digital scheme, you have to have synchronization. So I'm going to have you study a frame synchronization approach, which I haven't even actually built up yet, but I know what I want to do with it. The third problem, we'll look at digital modulation, basic digital modulation, and it's going to be just amplitude shift keying, which I referred to earlier, and likely it will have binary phase shift keying involved with it too, but it will be at a fairly high level. It'll be a bit pipe, basically, where you send bits in and get bits out at the end, and what you'll be able to do, and I haven't decided on this yet, you'll be able to wrap the PCM encoder and decoder around the outside of the link. So you send analog in, gets converted to a digital stream, then it goes through the link, transmit to receive, and then it comes out and hits the PCM decoder and brings it back to analog again, and then you can listen to it. And we'll be looking at the PCM stuff today. It's not something that you have to write up because it's already in Scikit DSP.com. It was added to that from the very beginning. So this is what the first problem will do, and it gives you an idea, though, of what all these problems will involve. It'll involve some block diagram, and also I'll look at the block diagrams that are in set number 6 too. It's a theme that communications engineers live with: block diagrams. What explains the system, what makes it work, and you can have high level, you can have detailed block diagrams. In the space radio project I worked on for Blue Origin a year ago, we were trading block diagrams around a lot. I would show them at meetings. Other people that were doing the FPGA side would show their implementation in their rendition of a block diagram that was more bit specific, register specific, and I would show mine with diagrams that look more like this. So what this block diagram does, and like I said, this was actually taken right out of a lab experiment from Real-Time DSP. We had a board, a microcontroller board, a Cortex-M4 microcontroller. Is everybody familiar, at least to know that there's a series of microcontrollers called Cortex-M series? Because that's actually what you've used already, right? So Cortex-M4 that I was using had the floating point engine instantiated inside the silicon. So we had 2 A to D converters on it, but in this case we were bringing in a modulated signal, and the frequencies are low in this project because this is what we operated at in real time. It's artificially low, but it's still representative of what you would do. You come in with a signal that's on a carrier at 16 kilohertz, and then you want to operate it on as if it's a complex signal, so you can do operations more typical, the way you would demodulate digital modulation, or even analog in this case, or single sideband, or any scheme for that matter. So the main theme of this is the next 2 blocks, the Hilbert FIR filter, which is put in parallel with a delay filter. So what the Hilbert FIR filter does, it creates the analytic signal, x hat, and then it's delayed by ND samples just simply because that filter is FIR and it has 31 taps, so 16 is the midpoint. It's causal, so to make it realizable / causal, it'll introduce a delay of ND samples, but then to put alongside of it the on-Hilbert transform signal, and this is now the analytic signal part, very similar to the homework problem you turned in. You just delay it so that the 2 wave fronts, you want to think of it that way, are aligned with each other. So it's just a pure delay. And that gets explained. You just have to put things in order to process the signal. So now we have a complex envelope or a complex signal Z, and we can envelope detect that, for example, by just simply taking the absolute value of it. That gets us back the envelope that we've talked about, the R of T or R of N in this case. And then for recovering amplitude modulation, I just have a digital DC block filter in there to remove the bias that you have from the envelope detector. And then you can look at it. And I haven't decided exactly what tasks I'm going to have you do, but it's not that elaborate. It's just some type of signal characterizing the frequency responses and things of that sort. The Hilbert filter is not perfect. If you remember from the lecture, the Hilbert transforming filter has, its main feature is it has a phase shift of 90 degrees, and it's flat in frequency. Ideally, it would be perfectly flat over the band of interest, but it would phase shift everything uniformly by 90 degrees, and that's the design of the digital filter itself. I think I might have pasted some code in. Yeah, I did. This will be in the final version of it, but you can see right there I'm using a function in the scipy.signal called remez, and remez you can design, you see there where it says type equals Hilbert. So I'm saying build me a digital Hilbert filter, have passband and stopband, critical frequencies, and then you get to weight the bands, and I'll have to talk a little bit about that in the write-up here. In the design of the filter, this happens to be a very nice design for getting a flat passband response rather than a response that runs from close to DC up to the folding frequency. It will be centered right over the carrier frequency of the signal and provide a very flat response. And of course, it doesn't have any group delay that's not constant either, so it's pretty ideal. And it's very efficient to get a flat pass band in a narrow band out of the 0 to fs/2 pass band, but it does it with only 31 taps, so that's very efficient from a implementation standpoint in a DSP engine. Nominally 31 multiplies and 32 adds, or I guess it's 30 multiplies and 31 adds. So it's pretty efficient from a resource usage. You're implementing it in Python, so you don't have any sweat about that. You can do it in double precision, which is what Python does natively unless you tell it a different type. I don't know, has anybody investigated the fact that you have in a NumPy array, you can define a D type, data type. So the data types you can define for an array can be anything that you're familiar with from coding in C. It can be an int 16, a uint 16, a float 32, a float 64, so a complex 64, et cetera, et cetera. Does that matter? Most of the time at the high level, we just work with double precision, but if you want to model more accurately something that's going to be implemented either in FPGA, or in this case it was on a Cortex-M that had 16-bit floats, or 32-bit floats, I mean, then we would do it that way. I guess there were 16-bit floats. And then there'll be tasks, and then at the end of the project, usually what I've included on these projects is I'll have a set of hints built right into the assignment sheet itself. And then this is from a different project entirely, but there'll be a rubric so you know what each part is worth point-wise and so on. So just something to be thinking about. I'll obviously announce it when it gets out there. Now we'll look at the exam for a little bit, just because I'd like to go through some things. I've graded, like I said, all the way top to bottom, 3 whole papers, and I've graded parts of 5 or 6, I think, because just to let you know that I may be harsh or I may be lenient, I try to be consistent. So what I do is I look at like problem 1, I said, wow, I'm getting a huge variation on this. I better do a sampling. I better look at problem 1 of a bunch of people to see what's going on. And I did that for a couple of other problems too, just to get a sense for what I feel like is how the mean performance. What is mean performance, though? None of you are a mean. All of you are an individual, right? You're a unique person. But so this problem I had used before. I modified it slightly, but I just said, let's consider a periodic signal. And I picked a shape on purpose to be something that would be easy to integrate. The whole idea was you've integrated exponentials all your integration life. I'm just saying that with dry humor, but it's a nice function that integrates easily. So I just said e to the t. This is the shape of it. It looks a little bit like a sawtooth function, but it's not because it's got curvature in it. It's very special. It has a period of 1 second. So everything kind of falls away mostly. So the idea was, using that theorem, you would isolate one period of this waveform and let that be p of t, and then you could create the whole periodic waveform by superimposing time shifted by the period p of t's, and that then Fourier transforms nicely using that theorem that we talked about in class. So your first objective is to go after p of f, the Fourier transform of one period, and then plug it into this theorem down below here and get something like this. So the integration of e to the t on the interval 0 to 1 is the integration that, from what I've graded so far, maybe one person did it totally correctly, but just forgot things, just did careless calculus things. I did it. I just combined the two exponents together, and then I know I have to do the antiderivative, or whatever you called it from calculus. So 1 minus j 2 pi f is what's going to sit down below there. And why is that? That's because t is factored out of this. So then I put in the limits, and I get this. And then I know t naught is 1 second, so I'm just going to sample this function every, at a 1 hertz rate. I'm going to replace f by n over t naught. That was the way the formula works. So I've got 1 over 1 out front. I've got n over 1 for f. This looks, dimensionally, it looks very strange, but it's just because 1 second and the inverse of 1 second is 1 hertz. So everything kind of just is very simplistic. But that's what you get when you put it all together. And I just went ahead and said, let's look at the DC value. And I said, it falls right there. And I said, eyeballing it, I said, that looks like the average value of that waveform approximately. If you'd say half of the area is in this spot here, and then the other half is in that upper triangle type shape, that looks like the average value. You know what I'm saying? Trying to get the mean value of that waveform. Then the second part was to just, totally independent actually, is to just say, let's find the average power, and that's actually easier to do. You just plug in p of t and take the magnitude squared of it, which would be e to the 2t, and then do the integration on that, and you get 3.1945 watts. What I did when I was checking them, at the beginning of the semester I talked about Maxima and WX Maxima, another free piece of software that can do symbolic. It's basically like the calculators I saw a lot of you using. A lot of you had TI, CAS calculators, right? Still pretty popular calculator. So this is a CAS, computer algebra system, that runs on Mac, Windows, and Linux. And I just simply said, integrate this thing for me, and it gives me the answer. The percent E is just a symbolic for saying that's E in mathematics, and the percent I just is square root of -1. But other than that, it does it perfectly. I then put in a plotting function here that could just plot the magnitude of that, and that's what P of F looks like. And then if I sample P of F every 1 second, those are like the Fourier coefficients that would be coming out in our expression. So it actually has a very strong, a large DC component, obviously, but then it drops off fairly rapidly. It doesn't have a behavior that's what? It has every harmonic present, so it's not odd half-wave symmetric. Do the integration of the power. Okay, so now that that was over with, I expected to see things start to get much, much better. And the papers I've graded, they did. Obviously, this was like standard playbook. And for those of you in the lab, and now we have the majority in the right now here today are all in the lab. So you had seen this in the lab probably a lot, right? You were taking measurements on waveforms. So everybody fell in line really well with this part. The spacing is related to the period, so 1 over the spacing is 5 megahertz. That's the period, so it's 200 nanoseconds or 0.2 microseconds. The duty cycle, we have to get what tau is, and tau comes about by knowing that we have our first null at 1 over tau, frequency-wise, so that's 25 megahertz. So tau is 1 over 25 E6, and then putting the ratio tau over T naught, we get a duty factor and our pulse train of 0.2. So it's on for 0.2 seconds and it's off for 0.8, well, not 8 seconds. It's on for 20% of the time and off for 80%. Now switching things up, this problem was a problem I think actually is in the book somewhere. I'm not positive, but I had used it before. It's just getting the output of a system that's got two sinc functions going into it, so those transform into rectangular spectra because of the duality property of Fourier transforms. One has a base width of 2 and the other one has a base width of 6. The filter itself has a 2 Hertz base, so when it filters using the convolution theorem in the frequency domain, this product becomes pi f over 2 because this is wider and this is narrower, so it reduces the bandwidth of the second pulse and it maintains the bandwidth of the first. So conveniently, I didn't draw in the pi over here when I was editing. I'll probably fix that. I should have capital pi of f over 2 in here, but they combine together to be 17 over 6, which for some people that was the answer, but they forgot they had to square it because getting the energy requires a square. This was Parseval's theorem for energy signals, but you just have to square it and then you multiply by the bandwidth, which is 2, and you get 16.05. Next problem, and that problem worked pretty well by the ones that I've graded, so I'm expecting that to hold true. Next problem was just a delayed system. It's got two impulse responses, one that's delayed out by delays 4 seconds, the other one delays 8 seconds. And I said a two-path communications channel. So this is in the business of doing terrestrial, cellular, networking, or even networking with Wi-Fi. This is where you have a path that has two, what would be called specular paths. You have two different types of propagation that can occur when we're close to objects on the ground. A specular path is when we have just a focused, the signal travels and hits us, and it's just seen as the propagation delay time. A diffuse path is when we have all kinds of scatterers and we get many rays of energy that scatter all around it. But in this case, this would be a two-ray path, 4 seconds and 8 seconds, and a characteristic of this sort of COM channel where you just have two specular paths is multipath, because we know from physics and common sense, when you have one signal delayed by one time and the other one delayed by the other, what's going to happen? We're going to get some constructive and destructive interference. Is that right? And when we switch to the frequency domain, we know precisely what's going to happen is that we're going to have a certain frequency, and we're going to have this occur over and over again where we're going to have nulls in the response, because we're going to hit certain frequencies where they totally annihilate. The two paths annihilate each other. So we get this null type spectrum for the signal, or for the frequency response. All you had to do to get the answer to part A, as I've been grading it, this is the answer right here, h of f. But I carried it on further because I wanted to get ready to do the sketch in part B. So the papers I've graded, some just wrote the top answer there, and that's fine. That's full credit. But getting ready for part B was important, and I would say of all the problems that I've looked at in this, almost everybody knew that they had to do something more with this, and they started to fumble with it a bit. I know some people got it correct, but so what do I do when I see, and this is a standard trick in this sort of problem. You have two complex exponentials. I'm just curious, because I'm going through this now, what does your mind see if I want to simplify that? If I know there's going to be constructive and destructive interference, and I'm wanting to figure out where do I have nulls in the frequency response, you look at that, and what grabs me is I say, there's a plus sign in the middle, so if I do factoring, what should I be able to pull out of this? A sine or a cosine? You know, remember, I'm thinking of Euler's identity now. When you have e to the plus j plus e to the minus j, that becomes a cosine, right? If you had e to the plus j minus e to the minus j, then you could form a sine out of that. But this, it should grab you and say there's a plus sign in there. So what I do then is I say I'm going to pull out, and I think I still have a typo in here I have to fix. I had minus 16 pi f. I wanted to pull out, let's see, what did I do here?
The answer to A is wrong.
The answer to what?
The answer to A for the h of f for the e to the negative 16 pi f.
Well, it's 8 and 16. So I know that's right. I'm just looking at my factoring now, because I wrote this down in a hurry, and then I started grading, and I said, wait a minute, I didn't do this right. So I looked at it a second time. But I will, I'll go back and see what I did here. I wanted to pull out e to the 8 pi. No, I wanted to form this into a plus something and a minus something, and then I wanted to have the rest of it factored out. So I think this might have originally been what happens if it's 12, because I thought that's what I had originally, and then I convinced myself that I didn't do it right. If I factor out e to the minus 8, and then I factor out a little bit more, halfway between 8 and 16 is 12, right? So if I made that e to the minus 12 pi f, then what I'm going to be left over with, I'm going to have an e to the plus 4 pi f, and when I factor out the e to the minus 12 pi f from this term, I'll have e to the minus 4 pi f left over, right? Am I seeing that correct? So that's what I'm going to have in here, and then I'm going to have, this becomes 4, and then I get a different answer. I get 1 quarter instead of 1/8. I had that originally, and then I convinced myself that I wasn't doing it right. But I will see everybody made, well, the papers I've graded, nobody gave me the same answer. So if I was trying to figure out what was the right answer by looking at your papers, I wasn't getting any help because I was getting different answers. But I will resolve that, obviously, in the grading. But still, the idea was I wanted to balance. I wanted to have a plus something here after I factored, and then I wanted to have a minus something of the same number so that I could combine that into a cosine. And then that's why there's a 2 in here, because I have to put a 2 in the denominator of those two exponents from Euler's identity, and then there's a 2 that pulls out in front. So the response is going to be, and this is embarrassing to me because this is what I had in my original answer. It wasn't until talking about it here that I was able to unravel it. Keep that in mind. Sometimes when you're presenting something to your manager, you might not be able to see the mistake until you're talking it through with somebody else. Has anybody ever had that happen? All the time. Okay. Yeah. So we're human, right? We make mistakes. At any rate, it's still the same idea and response. It has nulls, and the lowest frequency null is what I was thinking about. And if you're doing communications, at a much higher frequency, this null might happen with a certain propagation delay difference, and it might seriously impede your communications because you'd be passing a null through the passband of your signal, and you'll be annihilating things. So that was the idea with that one. Okay, looking over here at this one, this was just saying I have this, it looks like a double sideband signal, and that was the intent, and I'd like to process it And one way of processing it would be a coherent demodulator, but remember, I wasn't giving you a problem on chapter 3, I'm just giving you a Fourier transform problem. So I said, what happens if I multiply by e to the j 2 pi f naught t? I know that's the complex frequency translation theorem that allows that spectrum of the two triangles to either shift to the right, left, or to the right. So there's two options you can have here. You can shift it up or shift it down. The idea, though, is that the signal of interest is going to pass into the passband, and so it's going to end up, you can end up with one copy of it in there, and then one copy is sitting either over here, or if I picked to shift the other way, I'd end up with a copy here, and then I'd end up with another copy over here. But this bandpass filter is sitting in here, so, low-pass filter, so the low-pass filter sits in here, just like I've drawn down below here, and it passes the signal of interest centered at DC. And it has a total bandwidth of 2W if you take into account negative and positive frequencies, but in terms of a low-pass bandwidth, it's W, just like that we saw in chapter 3 for single sideband, or double sideband, I mean. So it's just to give flexibility. Now, one of the things that's a little bit strange to think about, this signal will be complex. So in the computer with DSP, this is not a problem. If you were doing this in analog hardware, you would actually have two different coax cables coming out of this operation. If you multiplied by this guy up here, this would be, from Euler's identity, it would be cosine 2 pi f naught plus j sine 2 pi f naught. So you'd have two analog multipliers, and you would have two outputs, and when you combine them together, you'd have a complex signal, and then you would have to, say, feed that into two A to D converters, and that would be a way of getting a complex signal brought down to baseband in a digital receiver. That lab, the project problem we were looking at moments ago did it a different way. It used a single A to D, and then it does the Hilbert transform to get it into a complex baseband signal inside. Just showing you there's variabilities or varieties that can happen. So I modeled this one. I have to go back and repeat my model just to check it out. Okay, this problem, everybody drew this picture correctly. Some people were forgetting to indicate the period, but it's pretty obvious. It's 6, because you see that right up here. So it's just a periodic train of right triangles. And the idea was to just find the average power in this waveform. Again, I picked something that would be easy to integrate. The right triangle has just got one side that you have to worry about. 1 minus 1/4 t describes that interval on 0 to 4 seconds, and then you have to take the magnitude squared of it. Remember, there's a cross term, and then put it all together. You get 0.222 watts out of that. Next problem. This was like some things I think were on the old quizzes, I'm not sure, but it was a power spectral density that has a DC component of 10, and then it has two complex sinusoids, one at 20 hertz and the other one at minus 20 hertz. So you just, if you want to integrate the power spectral density, that gets you the total power. This was in a homework problem I was grading from set number 3. So it adds right up to be 40 watts. I think everybody had this one correct. Even the person that got the lowest score I've graded so far. This is where the pedal went down to the metal, and it was just like cruising in high gear at that point. And some of you maybe feel the same way about it. Inverse Fourier transform, you could write it out formally like this, but you know that the 10 delta of f becomes just 10 DC component, and then each one of these becomes a complex sinusoid, which then forms a cosine again. And again, I saw this worked really well. The nonlinearity problem also worked really well in the front part of it, to see that when you look at x cubed with a cosine, you apply trig identities twice, you get the term of interest is this one right here. That's the 3f0 term, and you get a 1/4 out in front of that. So when you go down to compute the power in that third harmonic, it's going to be 1/2 times the amplitude squared. So we have the 1/2, well, we have an extra 1/2 term in here. Let's see, what did I have in here? I'm not sure why I have the 0.5 in there. I'll take a look at this again too. But at any rate, it's just going to be the magnitude of this component squared divided by 2. So this was the answer that I got, but maybe I have to go take a look at it again. Then the last problem, everybody had this totally right. It's just seeing that if you're looking for a distortion-free, you want both constant group delay and flat frequency response. So it's 30 megahertz, and then 50 megahertz if you mostly were interested only in the amplitude response. This was on the old quiz, so that's it for now. I will get these back to you when I get done and when I fix things that I'm concerned about maybe I messed up on.
Should be 8 to the 6th power?
Yeah. No, wait a minute. You're probably right. I definitely was doing this in a hurry, but yeah, you're right. This will be to the 6th power. It'll get resolved, and the nice thing about electronic grading is I can fix anything I want to by just erasing it and writing it again, and then going to the spreadsheet and fixing it. So that's why I don't push out solutions until I've graded the papers, because I usually will find errors, because I'll start seeing inconsistencies between what I do and what other people have done. Then pretty soon I'll say, wait a minute, this is the right answer. Okay, so any comments or questions? I mean, you're going into spring break. I'm going to work on this afternoon, but I'm going to clean up some other stuff. Obviously, I'll clean up any errors that I made here and get it graded out, and I'll push back set number 3, which that was worth 55 points. Quite a number of people got 55 on that, but some people still aren't using Python very effectively. And wow, this is something that also bothered me a lot when I was just grading that homework. The average is 43.8 on set number 3, but what brought it down is there are still people not working the right problems. I don't know what's going on, but I say drill, problem, or I say problem, which is the way they're written out in the book. And I had probably about 3 people that worked all the wrong problems. Any of you in here give any idea why that keeps happening? Because I thought that only happened in the first set, and I thought everybody was figuring it out after that, but I saw it again. Okay, the other thing I want to look at, which I can't look at since we don't have the internet, I can't look at, well, wait a minute. I might have it on a thumb drive here. I wanted to look at the homework, because it's all on stuff we've talked about already. So let me see if I can make this work for me. I ended up going back to the old-fashioned way of doing things. I was relying on iCloud and OneDrive on my various computers, and it was just started to fail me. It started to not synchronize, so I went over to Best Buy and bought a new USB-C flash drive just because it's the old-fashioned. It was called the SneakerNet, right? At least that's what I remember it being called. So I think it's sitting in here. So I'm having you do 3 problems. This maybe is my mistake, but because it's definitely not a simple grade to get through these. But of the 3 problems, the first one involves this block diagram. So this is an alternate way of generating single sideband. It's called Weaver's SSB modulator. It's something that would be more amateur radio focused or legacy focused, but the reason why I'm having you do it is you get to work a lot with trig identities. So what you do in this problem is you put in a simple message signal that's composed of a tone at FM hertz. It's less than bandwidth W, and then you're going to multiply it by, this is a transmitter now, so we're going to generate single sideband. So what should we be looking for at the output? We should, if we were to draw a picture of the spectrum, we should expect to see, if our carrier frequency is FC, sorry, I'm not drawing very well with my mouse, but we would expect to see either this tone shifted to FM above FC, or if we flip the switch in the other direction, we're going to see it shifted below by FM. And this will not be a fuzzy line. It will not be a simulation ambiguity. This is all the exact math. So assuming the filters are ideal and they work as expected, and the 90 degrees phase shift works as expected as an RF component, we're going to get, depending upon which sign we choose right here, plus or minus, it's either going to be a signal at FC plus FM or a signal at FC minus FM, just a single cosine wave. So that's what you're trying to drive for, and you're just working your way through this block diagram. So you go through the minus 90 degree phase shift just converts the cosine into a sine. So this is multiplying by sine of that argument. And the ideal low-pass filter, don't get confused, that low-pass filter has a bandwidth which is at W over 2, so it will block signals above W over 2, but yet the bandwidth can be up to W hertz. So what you have to set in your mind is that we're shifting things by W over 2 in this first multiplier, and then the low-pass filter will throw something away and keep something. Then we're doing it a second time, and the plus minus there goes with this plus minus for upper or lower sideband, and then it combines together. So you're going to have a bunch of trig expressions that you'll write out, and it seems like a really, really big pain in the butt, and it is. But I think it's good to just see this as an example of how you can prove or disprove that something works. So just jump into it, and if I was doing it, what I would do is I would divide the work into 2 portions. I would have following the signal flow along the top, so look at the output at each point along the way, and then follow the signal flow along the bottom, the output at each point along the way, and then you get the 2 final outputs, which would be here and here. You'll have terms in here which are going to presumably combine and then also cancel. So you're going to get, if you add, you're going to get the upper sideband, which will be the red one. If you subtract, you're going to get the lower sideband. Does that make sense? I just think it's a good thing to bear with it. If you built a simulation model for this, which was Project 1, a DSP version of this model, but I'm abandoning that, you would see that it works, but it doesn't work perfectly. Now, so if this was not a perfect low-pass filter, what's going to happen is you're going to get, say, red will be strong, and you'll get a little remnant at the green, and vice versa. Does that make sense? It'll be like 20, 30 dB down or something like that. 321, I don't remember exactly what that is, but 3 problem that I'm supplying you is another block diagram problem, and this is just working with frequency mixing, or super heterodyne concept, which is the moving frequencies from one location to another. So this is a block diagram that came out of a paper for an integrated circuit, RF front end for Wi-Fi, and this just also introduces you to what the standard Wi-Fi spectrum looks like at 2.4 gigahertz, something that you've been living with pretty much your entire lives, I think. So you get to see what are the channel numbers, what are the bandwidths, and what are their center frequencies. And then your main thing is to come up with 2 options for the local oscillator that will bring this down from whatever channel it's at to 160 megahertz. So in this design, this RF chip that was in this article said it's going to be a surface acoustic wave filter that's off chip, but the mixer, the low noise amplifier, the IF amplifier, and then these 2 IF mixers, low pass filters, and variable gain amplifiers that would drive 2 A to D converters are all on chip. So this creates a front end for a Wi-Fi receiver like you'd have in your cell phone, laptop, etc. And you would just be selecting which channel, which Wi-Fi channel you're going to tune in. And the interesting thing about the way the Wi-Fi standard, and it's been revised, it's continuously being revised, but what do you observe there? They overlap, right? That's just the way they were developed by the IEEE and the Standards Committee, that they overlap. This was a project that I wanted to add another lab into the lab to go take the field foxes around with the antenna that I think I showed you one day, and just camp outside various buildings on the campus here and see which center frequencies have been assigned from the 2.4 gigahertz Wi-Fi by campus IT. And I guess there's, pardon me?
Cool.
Yeah, be an eavesdropper. And then there's also Wi-Fi nodes sitting around on the spine, right? At least that's what I understand, but it'd be a map. I mean, I'm sure there's a map of these assignments in IT saying this is how we have our wireless router set up, and this is where how we're distributing the 2.4 gigahertz portion. Oops, didn't want to do that, but so that's fun, I think. But is it fair to have fun when you're doing engineering? I think it is. So I'm going to unmount my disk so I don't my drive so I don't forget about it. I had not bought one of these, especially a USB 3 one. I actually didn't have but one, and it kind of fell apart on me. These things are much faster than they used to be. They're not that expensive. So I was spending more time trying to get syncing working on my iCloud Drive stuff, and I just decided I would take it out of my life for the time being. So this is kind of the old-fashioned way for me. Okay, back to the notes now, where we have been hanging out. We had one last topic that I started on last week, and that was interference. So the interference term that we're talking about is, if I can get this to go for me. So I'm just posting out the interfering term as being above say, an AM signal. But it could be single sideband, it could be digital modulation, it could be FM modulation, because we'll review this interference scenario when we go through angle modulation. But now we're looking at linear modulation. So we're putting a jammer, just a single tone, sitting it close to our signal of interest. So in the model here we have an AM signal represented. So we have pure carrier, and then we have a single tone times omega C. Now, just to make sure you keep thinking, why am I doing this? I'm picking something simple to analyze. I just want to understand what tone modulation, when jammed by another tone, will turn into. I could pick something more sophisticated, and I'm going to do that in a demo here in a second. But I'm just picking something that the math is easy on, just some single tones. So the AM signal is composed of tone modulation, and then the jammer is a single tone jammer. So I carry it out. What's going to go on in the receiver? So I'm going to suppose I'm going to do a coherent demodulator. Why do I pick coherent initially? It's just easy way to go for understanding what happens with the jammers present. So when I demodulate with a coherent carrier at omega C, I'm going to bring these two sidebands down to pass through a low-pass filter. And I'm also going to bring that jammer tone down to pass through the low-pass filter. Now, what could happen, and what should happen actually, if we're designing our receiver front end properly, this signal, in the case of the coherent demodulator, should not make it through the low-pass filter, right, that we use for coherent demodulator. We multiply the received signal by cosine, and then we keep the signal at DC and reject the double frequency and so on. So in this case, we have this jammer, which is a ways away from our signal of interest. So in a practical setting, that interference tone should be brought down or eliminated. In theory, it would be eliminated, right, if we're using an ideal low-pass filter. But if we think about our real design might have a filter that has, I'm not drawing a very good picture, has some skirts on it that don't roll off fast enough, so it's going to let some of that signal come through. Now, if it's an audio, analog modulation, this might be present, but the audio amplifier is not going to do anything for us. It might be present actually in the waveform. Even if it made it through the audio amplifier, we wouldn't be hearing it because our ears wouldn't hear it, right? If it was digital modulation, it would definitely be an issue. So we want to avoid having any interference get in. So we generally try to remove that with filters, but the closer and closer this jammer gets, if it moves in really close, or if it moves right inside the modulation bandwidth itself, then we have a serious problem. So how can we kind of see what's going to happen? Suppose we're doing an envelope detector, but yet the carrier signal is very strong compared to the interference. The interference is just weak compared to our carrier signal. If we expand the interference using trig identities into a cosine term and a sine term, and this, I think I opened this up yesterday. Yeah. Keep these things handy because you just want to be able to plug into them. You'll eventually get them partially committed to memory, or maybe you were an expert in high school, which I was not. I didn't know what to do with trig identities in high school. I'm like, what are these for? I mean, I knew what they were for, but I just didn't want to. I didn't see the value in them. Now, of course, I definitely do, but at any rate, so I just use one of those trig identities, and now what I'm doing is I'm expanding the interferer, which is already relative to the carrier. Go back up here to this picture and say we have the jammer at an interference offset from the intended carrier, so it's already set to be expanded like this, and then we can bring that into our format for doing complex envelopes. We'll have all the cosine terms are lumped together, and then we'll have the sine term, which is from right here. That term will come in with a minus j sine, but we're multiplying all of this by e to the j omega ct, and then we're taking the real part. So the real part is thrown in there too. This idea of the envelope expansion is just to get it into a form where we can see what the real envelope looks like. So we see the real envelope, or the complex envelope, looks like. It's going to be composed of all of these terms, and then the imaginary part is this piece. And when we take the real part, this all reduces back to where we started from. But now we have the envelope, and the envelope detector recovers the magnitude of that complex envelope. And if we look at what it's doing over here, we see this happening. We have, to get to the envelope, we take the square root of real part squared plus imaginary part squared. But we had, this was from our first encounter with this, we had 1 plus wigging out on me. Okay, what's going on here? When in doubt, just use my mouse again. I see what happened. So the square root of 1 plus x is so this is the binomial expansion, and we said before that if we can factor that complex envelope in such a way that we can pull out a large constant, which in this problem that large constant will be this, we can factor that out, and then what's going to happen, and I'm just telling you this, what's going to happen is we're going to get, in the end, when we multiply it back through again, we'll get AC plus AM cosine omega m, and then we'll just get the jammer with amplitude AI. And that's because we're dominating, in this case, by the strong carrier. And I'll draw a picture of that, because I think that helps explain it better. So probably didn't exaggerate that enough, but the idea being that the interferer is sitting there up above the three components from the AM modulation. If that carrier is really strong, it's going to look like our envelope detector is just going to recover all of the modulation, and it's just going to incorporate this interference just as a linear term, because the envelope detector will say that it's being dominated in this expansion with binomial expansion theorem to just get 1 plus 1/2 x, and that's what we'll recover out of this. We're going to recover this. This term is going to dominate. This one will get buried because it has AI in it, and AI is small compared to AC. But now if we take the case where it's not moving right now, and I don't understand what just broke out. Now if we take the case where the jammer, it can be made large relative to This is how I grade papers too. This is the same tool I use, but it's definitely flaking out on me. Has anybody else used this? It's not, there's a free version. It's called Drawboard PDF, and it runs on iPads and Macs and PCs. At any rate, if we make the jammer very large compared to the carrier, then what happens is, as I say here in words, it looks like everything in our picture here looks like I'm just raw. Why is that not moving? So the jammer is sitting really tall, and what it looks like we're doing when we talked about single sideband demodulation with an envelope detector, we could reinsert a carrier, which is what the jammer is playing the role of, and these all look like lower single sideband tones. So the detector, the envelope detector, just says, oh, I will recover those tones relative to this reinserted carrier, and the user will just hear all of those things summed together. Does that make sense? I could do the math on it. It's tedious. I'm more interested in just drawing the picture like that and saying, we saw that already, that an envelope detector can be used for single sideband. If we reinsert the carrier, which is what is done, say, in single sideband receivers, reinsert the carrier, make it very strong. It's not present when the signal comes at us, but the jammer is behaving that way. So when it comes into our receiver, it looks like this has been applied as a reinserted carrier for us because of the jammer, and then those things get demodulated, shifted in frequency from the jamming tone. So I built that went back to the Jupyter Notebook, and I was going to do a separate example, but I didn't spend a lot of time on it because I wanted to get back to grading. But what I did was I went to the demodulate AM, and when I transmit the AM, what I'm doing is I'm putting in a tone that's 5,000 hertz above the 24 kilohertz that we were using before, and I'm giving it an amplitude of 5. I did this last night. I'm going to do it with 10. I'm going to make it much larger than the carrier amplitude by a factor of 10. So now we see in the envelope of the signal, and this is now pretending this is our received signal. We look at the spectrum. There's our AM signal, the carrier, and this is our jammer right here. So now I'll take that down and demodulate it over here. And there it is, but now this, for those of you in the lab, this is looking a little bit more like the lab experiment where you've got spectral information kind of flying all over the place because of the action of the jammer and then the nonlinearity with the envelope detector. So we're getting, this is our AM signal at baseband, but it's been shifted up in frequency because of the jamming tone, and all this other splattering of stuff is just because of the strong interference. So if I go ahead and recover that with the low-pass filter, this low-pass filter, there's our AM, there's a strong DC component there. And I was having this problem last night where my audio was not working properly. So let's see, how did I solve that problem? What I wanted to do was set set the audio to run out through the HDMI, but I'm sure it's not necessarily going to work at all. So I'm going to cut to the chase here and go ydd.wave, and I will just simply look for that in over here. And it's not playing. What did I not do right today that I did right before? I got this guy selected. Does this look right? I should be hearing it through the Extron is this interface, so it should be playing out through the speakers which are in the room. Okay, it's there. It's so far away that I can't even hear it. Could you hear something? It was dominated by high frequency tone. So now what I'm going to do is I'm going to make the jammer get closer, which means I'm going to be definitely in harm's way. I'm going to take the jammer tone down closer. Now it's very close to the AM, and let's see what that does. So I will go through the envelope detector. Go through the low pass, which has got a bandwidth that takes stuff away anyway. Okay, so this tool is file got locked when I wrote to it again, or maybe it didn't write to it, so let me write it again. So that tone is the jammer's offset from the carrier, and then the speech was very distorted sounding. It should appear shifted in frequency, but it's kind of hard, in my mind, to sort out what's happening. But everybody good with that idea? We're definitely pressing it into a hard life. If we were to take the jammer amplitude way down, then it would all of a sudden the signal would come back up. And the best story I could tell on that is if you were to go past the antennas for an AM radio station and be listening to a station that's pretty weak, and then you were driving past this tower that's close in frequency to the station you were listening to, you'd get jammed very heavily by the proximity, and it would take your radio, your signal would get wiped out by the strong interference. In the lab, you'll be doing some jamming of each other eventually, in the next experiment, actually. Okay. I'd like to resolve why this is not working for me. I don't have my mouse working, I don't know why. And I don't know why this thing is sitting in here because it's not moving. So something wigged out with my tool for whatever reason. But we're going to take a break here pretty soon. I'll just say now what we're going to do is we're going to switch to digital modulation or digital forms. And the first thing is a quick review of sampling theory. And then we'll add to that bandpass sampling, something that you haven't seen before. So this is typical low-pass sampling, where you take an analog signal, take samples of it every TS seconds, and this is then the information that comes out of the ideal sampler. It's a sample values located on delta functions as an analog waveform, and then that effectively is encoded into a bit stream in an A to D converter. Talk a little bit about that in a second, but what do we know from basic sampling theory is that we'll assume that the signal has a spectrum which goes to 0 when the frequency is greater than W. That's our bandwidth of our signal. It cuts off at W hertz. And then the low-pass sampling theorem in the blue box there says if we sample at greater than twice the highest frequency, we can reconstruct and avoid aliasing. So we just keep Fs greater than 2 times the bandwidth of the signal, and then we can reconstruct from a low-pass version of the sampled waveform. And 2W is called the Nyquist frequency. W is generally less than Fs over 2, which is the folding frequency. That's half the sampling frequency. So we have those. These are official terms that you've seen before, starting in 2610, actually. To prove that the theorem works, we can go to the frequency domain by taking the Fourier transform. We can use that theorem that says if we have an ideal sampling waveform with the sample values, it will be the convolution now in the frequency domain, because the time domain, it's the ideal waveform times the continuous analog waveform, but it becomes sampled. So in the frequency domain, we take the spectrum of the analog waveform times the spectrum of the sampling waveform, which is now delta functions in the frequency domain, and you get the convolution with the delta functions just gives you the spectrum replicated up and down the frequency axis with the sampling frequency clock. So you have translates running up and down, and that's what the dots here are saying, that it's going in theory up to minus and plus infinity, but it's limited because the bandwidth of the sampler is finite. But approximately, this is a good model for it in an ideal setting. And if the frequency is 2, not greater than twice the highest frequency, then you get the aliasing when the signals overlap in the spectral domain. And if you're intending to recover with a low-pass reconstruction filter, now you'll get some aliasing in your signal. Okay, the last thing I'm going to do before we take the break. This just talks about the ideal reconstruction filter. But after the break, I'm going to talk about uniform sampling theory. But before we do that, I'm just going to show you a couple of demos that I wrote in an object-oriented basic language many, many years ago called Xojo today, Xojo. But I can animate things, so it's kind of fun to look at this. This is assuming that I have a sinusoidal tone, and I'm sampling it with a variable frequency and in a variable phase. So the sampling rate is always set equal to 1 hertz, but the frequency, the sinusoid, can go above 1 hertz. So here I've got the frequency very low, so my samples are looking like I can visually reconstruct it from the samples. If I go up to the point where I only have 2 samples per cycle, this is the folding frequency, right? So now I'm going to lose the ability to reconstruct it, and if I keep going up, it doesn't look like the samples mean anything. But we do know that there's aliasing there, and if I flip this switch, that's the alias frequency. But this is a mind puzzle, a mind-eye puzzle. If I keep increasing the frequency higher and higher of the sinusoid, eventually I'm going to get the alias frequency will become more obvious. In other words, this is the signal, and the blue dots are not looking like they're making any sense. But if I go up higher and higher in frequency, at some point, you're going to see in the blue dots that they do connect at the alias frequency. Following me? Because it's about ready to happen, depending upon how your eye perceives this. Keep going. I can see it right now. You see how the dots connect? They're going to be at a lower frequency than the red, but higher and higher. Now it's very obvious, right? So that's the result of this aliasing. And of course, if I keep going, now my samples are looking like they're getting very low in frequency, connecting the dots. And if I flip this switch, though, then you can see that this is the aliased waveform. When I hit the folding frequency, it flips, and it goes back the other direction. Another interesting thing you can do with this, which I think is kind of fun to play with, is if we go back to where we have just 2 samples per cycle, which is about there, what happens if I shift the phase? Can I recover right at the folding frequency? What were you taught in 2610? I think the theorem says you have to keep the signal that you're sampling less than the folding frequency. Otherwise, you can't recover it. Do you remember that nuance? So I move the phase of the input signal with this, and if I phase it properly, I get nothing, which is what you'd expect because you're right at the folding frequency, and if the signal comes in, it gets sampled and you get nothing out. I bring this up because I was teaching a short course here at UCCS to a community group of engineers that were wanting to learn about DSP, and I wasn't the one on stage at the time, somebody else was, and somebody in the crowd started arguing with him about sampling theory doesn't work, it's not true, and here's why. So I always think about that when I talk about this, because obviously you have to take it in the right context, right? If you don't obey the sampling theorem, you don't get it back. And it looks pretty ragged, but the low-pass reconstruction filter that we could look at does reconstruct it. And another thing about sampling theory is it would be a rare occasion where the signal that you're wanting to sample is synchronous with the sampling clock. Generally, the sampling clock is asynchronous, so it's sliding through. You can get right up to the folding frequency, and you will get something out because it will be asynchronously sliding through, and you'll be getting samples that are non-zero. So one more demo, and then this will set us up for what we'll talk about after break. This one looks at low-pass and band-pass sampling. So here, I'm going to slide the sampling frequency up. So I'm displaying down here Fs over B. So if I take Fs over B up to 2, then I'm just, at the Nyquist rate. So I get no aliasing. And when I lower this down, or I raise it up, I have more clearance for designing my reconstruction filter. If I bring it down, I definitely have aliasing in there. Is it making sense? Okay, now here's something kind of cool. I'm going to move that way up there, and I'm going to turn on a bandpass signal, a signal that rather than being low pass, where it's got spectral content, 0 hertz all the way up to Fs over 2 or whatever, it's a bandpass signal. So it's blue, and then the spectral translates are in red. And I'm 2.5 times the highest frequency, so I've got clearance in here. I could recover this with a bandpass filter, but now I can undersample, because watch what happens when I drop the sampling rate purposefully below Nyquist. It's at 2 right now, but I drop it down. I don't like that, but if I drop it down further, like there, I can recover the signal of interest by undersampling. And that's what the theorem talks about that we'll look at right after the break here. But This is a technique that's used in DSP radios all the time. And as a matter of fact, if I go to a narrower bandpass signal, I can even get away with undersampling even a greater amount. This would give me a little bit of clearance. This is like there. That's the limit. That would not actually be easy to accomplish, because in order to get the blue one back again, you'd have to have a very ideal bandpass filter. But in a digital receiver application, we don't go after the blue one. We'll go after one of these translates that gets formed through the undersampling, and then recover our COM waveform from that. But it'd be more likely at a rate, say up in here, something like that. It's called IF sampling is another name for it. If this blue was an RF signal, we could undersample it with a wideband A to D, and then we could take a translate that's right down here near DC and process that by shifting it with a complex frequency shift, center it on 0, and then work with it from there. And that's a very, very common technique, and it's called bandpass sampling or IF sampling. It's a standard technique. So I don't know if you ever thought that this could be possible, but it's interesting, right? You were taught that sample at greater than twice the highest frequency, but with a bandpass signal you can play games with it and do more. And it's utilized all the time now in radios, digital radios. Okay, we'll take the break and come back at around 9:45, let's say. Okay, I think I resolved why I was having problems with Drawboard, because I didn't have an internet connection and eventually decided it wanted to stop working for me. So I was able to get back on the Wi-Fi again. So we were just looking at low-pass sampling, and then I slid past reconstruction filter. But if you recall, the bottom line is that when you're using, say, an ideal low-pass filter for your reconstruction filter, you take the samples and you're convolving with an impulse response, and that impulse response is the sinc function, and that's the ideal interpolation function, to take the individual samples and then connect the dots and take it back to a continuous time waveform. So now let's just look at what the bandpass sampling theorem consists of. It's called the uniform sampling theorem for bandpass signals. It's written into our book, and it changes the definition of things slightly. It says here that we're going to assume that the spectrum of our signal is 0 for f less than f upper, but we then also have associated with the fact that this signal that has its upper band edge being fu, f upper, has got a total bandwidth of w hertz. So the theorem says that the sampling rate fs can be made equal to 2 fu over m. So it's not that it has to be greater than something. It's because, remember in the picture I was showing you how when you were undersampling you were getting overlaps that caused aliasing and things. You have to stay in a certain band. And in this case, this is a simplified theorem for saying this will work. So you take 2 times the f upper, which is like the Nyquist criteria, and then you divide by m, and m is the greatest integer less than or equal to fu over w. So when you plug numbers into that, then you can take a signal spectrum, and this is idealized spectrum, 2 to 4 hertz. So we say the bandwidth of this signal is 2 hertz wide, the upper is 4 hertz, fu over w is 2, so m equals 2, and fs is 2 times 4 over 2, or 4 hertz will work. And I actually have in the Jupyter notebook over here, get way down here, I have a section on bandpass sampling theory, so I have a little helper function in here which lets you put in a frequency axis that you want to use for plotting, put in the sampling rate, how many translates you want to show, and then it works from a catalog of a triangular shaped spectrum, and you get to say what the lower and upper bandwidth is in that spectrum. So as an example, suppose we span from -10 to 10 hertz, take steps of 0.01 hertz, and now we're going to put that in as our frequency range. We're going to set, let's just do it this way so I can get at it. FS, we're going to set the sampling rate equal to 10, and we're going to set the number of translates on display equal to 8, and we're going to assume that the bandwidth of the signal runs from 4 to 8. So I should be more than adequate from a low-pass sampling theorem standpoint. I'm saying it goes up to, I'm sampling at 10 hertz, I go up to 5 hertz, so 5 hertz is the upper band edge, 10 hertz sampling rate is exactly twice the highest frequency. So I see from this picture, red is the original spectrum, blue are the translates. And if you want to understand what's going on with this notation, if I was to put in, no, not that. If I wanted to draw more translates, I would just increase this number to say 16, and then I could let this go 20. I don't think I needed to put in 16. I didn't show this zoom properly. Let me not mess with that right now. I'm going to do something else. I'm going to get sidetracked. You can play a lot of games with this, but I'm going to now say, according to the problem we just worked on, the example we were just looking at, the F upper was 4 and W was 2. So I could modify this problem with a software tool that I wrote, and I could say let F upper be 4. And so I go back into this example. I'll set this equal to 4, and I'll set this equal to 2, and create the picture again. So now I'm sampling starting at 10 hertz. So I'm plenty high. The folding frequency is at 5 hertz, but now according to what we showed in the example, I should be able to set Fs equal to 4. Let's see if it works out. Remember, Shift Tab will tell you what the attributes are, so I'm putting in Fs equals 4. The number of translates, I'm not displaying enough frequency axis that 16 even matters, but so now you can see what happens is I do have translates that are landing down at baseband, but they're not interfering with my signal of interest. Make sense? I mean, we're saying we could recover with a bandpass filter, and we could continue to mess with that. Suppose I let this be 3. Now there's a lot of space in here, so could I work with 3 in this particular case? I don't think I can, but let's just see. The formula said M is equal to Fs over Fu over W, so I'll plug into that. F upper is 4 in this case, and I made W 1. The difference between these two is 1, so I have 4 over W. Wait a minute. No. Didn't want to do that, I just wanted to do this. So I have 4, and then I can divide that into, I'm just following the formula right now. I can say, okay, I have 4, and then I can put 4 into 2 times 4, and I should be able to operate with fs equals 2, is what this is telling me. So there's my original signal that's running from 3 to 4, and now I've packed even more spectral translates in from undersampling, but I'm still theoretically safe. I don't consider this to be practically safe because they're just touching, but you get the idea of how the bandpass sampling theorem works. It's pretty significant for software-defined radio that is now part of our lives. So. And we're looking at this picture live in Python, so I won't talk about that. So now that we've reviewed low-pass sampling theory, and that's really the rest of this discussion, the bandpass sampling theorem is so I could throw some examples out from the book or talk about a software-defined radio undersampling scenario. But the rest of the application in the rest of the chapter here is just sampling theory. So the first type of digital modulation or of sampling theory-based modulation is called analog pulse modulation, and it's known as PAM, pulse amplitude modulation. So you sample the signal. In this case, you sample it, Nyquist, satisfy Nyquist, and you're going to sample it with a sampling pulse of width tau. So rather than taking an ideal delta function in this original creation of PAM, and I think you guys are all too young to remember what I'm going to explain here in a second or two, but I'm going to find out who might remember this. PAM lets you send the analog waveform by just sending an amplitude of this pulse train that represents the amplitude of the waveform when sampled. And one of the things you can directly recover the message by just low-pass filtering with a ideal low-pass filter, and we can reconstruct, because we're going to get translates, even though we have the sync function envelope due to the using a pulse train, and that's causing this roll-off in here. As long as the pulse is fairly narrow, we don't get much roll-off in the passband there. So the idea there, ideal impulse train sampling gives you all the bandwidth, whereas this finite pulse width gives you some roll-off factor, but it's not too bad. And it's pretty straightforward. So what did people use PAM for a long time ago? And that long time ago depends upon your definition of long time ago, but I can remember flying in airplanes. This is where I experienced PAM in the life, where you would get a set of headphones handed to you, and it was not wire. Does anybody remember where it was a sound tube? It was not wire headphones, earbuds. It was actually, tubes. And you'd plug it in, it had a connector, and it was this sound tube thing, had two tubes that went in for stereo. Does anybody remember that? Okay. So you're just too young to have experienced this.
Children.
Yeah, exactly. But what they did with this PAM is they could send multiple analog channels down on this sound tube in the aircraft body. You could plug in your tubes, and you know that it was a tube because it went up to your head, and if you pinched it shut, the sound would get pinched off. But they could multiplex. They could do analog multiplexing of this PAM waveform. They could have like 12 channels of audio you could listen to on the aircraft through a sound tube. Sounds really crude, doesn't it? It was the way it worked. I mean, and you had a little selector knob that would change the multiplexing, the demultiplexing, and I'm pretty sure channel 0 was probably the pilot, how hearing your overhead instructions. That was the beginnings of that. The fidelity wasn't great. You got to think about how the sound was propagating through a tube. from some transducer somewhere in the guts of the aircraft. To me, I think back on it, I say, this is so primitive, but this was the beginning of in-flight audio using pulse amplitude modulation. Most of these we're going to look at are not the most exciting anymore, but okay, this next one does have wide application, but not for the application that it was originally maybe intended. Pulse width modulation says we make the width of the pulse proportional to the sampled analog waveform. So the way you have to make this work for a signal that's got positive and negatives in it, you have to put it on a bias so that zero width or near zero width corresponds to one amplitude, say the most negative, and then positive corresponds to the widest. But however you set up to do it. Most of you, if you played with robotics, have worked with PWM because that's how you control motors these days, is with pulse width modulation. But what I'm talking about now is the only thing relevant for speech communication would be a Class D audio amplifier, and some of you maybe have heard of these, or maybe you have one of these, I don't know. So then the Class D is, thinking back to electronics, you learned about classes of linear amplifiers, like A, B, C. Remember that from electronics? Class A is the device is always biased on, so no matter what signal you're giving it, it always stays in the active region and in the linear region. And Class B would do a push-pull kind of arrangement where one device would be activated on the positive cycle and then the other one would be activated on the negative cycle, and that gives you some power efficiency. Class C is used for RF, and it would basically clip the waveform a lot, but then you would reconstruct it with a bandpass filter and get even higher efficiency, and that's still used in SATCOM today. But Class D came along more recently, and it's actually not archaic. It's more popular today. That can be used with digital pulse width style modulation, or pulse interval modulation is another variation on it. So there's some of those things going on in devices that you might not even know that it's being utilized in. But PWM, like I said, is probably most popular in robotics for motor control. So pulse position modulation was another type that came along, making the position of a pulse in a sampling period vary from being early or late. So this is what PPM looks like. The pulses are sent, like I said, within an interval of the inverse clock frequency or the sampling rate. So that's PPM. When I worked originally in my first job at Motorola Government Electronics, which is now General Dynamics in Scottsdale, Arizona, I was working in optical comm, and another part of the team I was on was doing a PPM type optical system. But it was a digital PPM, and they called it PIM, I think, for pulse interval modulation, but they were sending their digital bits encoded into a position, and they had the laser set up so that they would send the laser at different time intervals. And then you would synchronize to a pattern, and then you would know what that time interval corresponded to decode it back into a digital word. So that was taking it beyond the point of saying it's just analog to analog. It's going to be actually quantized into various intervals, and then those represent, rather than an analog value, they represent a digital value. The next type is a family known as delta modulation, and then within that we have DM and then PCM, which is kind of the only thing that really is popular still today, would be PCM. But delta modulation, you encode the sequence, but they came up with this idea that you would take and digitally convert with a comparator. So to me, I don't know about you from your electronics backgrounds, but this to me is a comparator, something that would fire 0 or 1 depending upon the amplitude. But if you give it a bipolar behavior, then it's like our signum function, SIGN. It's going to represent the sign of the value, and you're oversampling it. And what you do is you sample that output and send that down the line as an analog signal that's taking on values of plus or minus 1. And then you feed it back with a step size parameter and integrate that, and you subtract that. So what you end up getting out of the operation is, think of the analog signal being the smooth line here, blue, and then the delta modulation is stepping up and down by step sizes to try to follow it. And then what you're transmitting is these plus and minus 1s, and these could be, digital values. They could go into a modulator, a carrier modulator of various sorts, but at any rate, this was called delta modulation, and it was used in telephony, and then there was an adaptive version of this too, adaptive delta modulation, which would control the step size depending upon what the signal is doing and what you need to do. There were chips made that did delta modulation too. Again, not really all that common anymore, but I suspect it's in legacy something. I mean, you guys are going to be on, I wouldn't say the hunt for it, but you're going to, depending upon where you take your job, you're going to land in something where you're going to be working on a legacy system, and you're going to say to somebody that's older than you, so when was this system first created? And you're going to go, what? This has been around for that many years? It's just the nature of how we do things, though, right? This was a simulation model I had in MATLAB, and the fact that it's still in the notes as an M function in MATLAB just says that I haven't really cared to do anything with it. You would be able to translate this to Python, no problem. I'm very much convinced of that. As a matter of fact, if you're still taking another class that uses MATLAB, is anybody doing that right now where they're having to do both?
All my classes.
Oh, really?
Yeah.
Okay, but you're getting versed at both, right?
We're getting what?
You're getting versed at the differences.
Python and MATLAB.
Yeah. It's valuable. It's very valuable. And C. You could learn C++ if you had to, so you'll say, you want to have that in your background. So
The industry actually really likes Python.
Who does?
The industry.
Yeah.
Every job interview I went to, they're like, Python?
Yeah, so what you're telling me is something I've known about for over 10 years, but yeah, it is cool. Now Julia, if I was making you use Julia, it's not nearly as common, and it may never achieve what they were hoping it would achieve, but I would love to have forced you to use it in one sense, but I realize it's not good for your overall career right now. It's just very fast, and it's amazingly fast, but most of the educational stuff I'm having you do here is not demanding. The stuff that you do maybe in industry, you're going to bump into something. You might say, I'll code it in C++ or I'll use Julia or something like that. And I did a project for one company in Julia entirely, and I delivered it to them because they wouldn't buy me a seat of MATLAB, and I just wanted the speed because I needed it for the type of simulations I was doing. And it was also a sales pitch on my part. I said, I want to do it because I want to make this get done faster. You only gave me so many hours, so I was trying to be good use of my time. So here's variable step size where you sense the power in the signal that's coming out, filter that. So this is doing a power calculation, and then it's going to a variable gain amplifier to control the step size. So this was the big innovation of adaptive delta modulation that came along. So now, let's see, didn't want to do that. It's amazing how freaked out I was. I didn't understand why this is working so poorly. It requires the umbilical cord. But postcode modulation is still very much in use, and it's the beginning of virtually everything in audio, in particular in soundstage. Everything would be done in PCM initially because it's totally bit true. There's no funky algorithm that's trying to involve perception of what's in the waveform itself. It's straight off the top, just digitizing at a particular sampling rate, number of bits you're going to quantize into. So in reality, it's an A to D converter. So we have a sampler, then we quantize the sample values into so many bits of resolution, so it becomes a digital word at that point. And then the encoding operation is just simply to take those bits and package them up in a particular format for digital. So equivalent would be, like I say here, a sample and hold, an analog to digital converter, and then a parallel to serial converter is what would happen. I mean, the way I think of an A to D converter from the beginning, and I used to teach electronics too, not here, but when I was in graduate school, it would take an analog sample and it would convert it into so many parallel bits. So you would have an A to D that would have a parallel interface output. And then who wanted to use that parallel interface? Nobody wanted to use it. They wanted to ship it as a serial bit stream. So then most converters today send out a serial stream, so parallel to serial converter. As soon as you do that, though, what happens, and this is what you're going to do in the project problem, as soon as you do this, serialize it, and then it travels a distance, maybe has to get reclocked or retimed or something further down the pipe, you're going to lose track of where the bits are, where the MSB is, where the LSBR is, and what you have to be able to do when you decode PCM is you have to make sure you've got the right bits aligned. You've got the MSB is maybe the leading bit, LSB is the trailing bit, or it could be the other way around. So we'll be talking about that here in a second. I'll do a demo of this. So the basic idea of the PCM is just a mapping with a quantizer, and this is just a 3-bit example that has 8 levels in it. So 2 to the 3 is 8, and you just make a bit assignment. So the red dots are encoded, straight binary. The most common scheme is not straight binary. It's generally 2's complement, which you've probably seen before in the microcontroller class. So you would encode the values into 2's complement. And if it's a unipolar converter, it only converts positive values, and then 2's complement doesn't really matter. But if you have a signed converter, then you represent it in 2's complement. I guess another format that was used along the way is called signed magnitude. Does anybody learn about that in microcontrollers? Signed magnitude just says you're going to take your package of bits that represent this, and you're going to let the leading bit represent the sign. And so if it's a 1, it's a negative value, and if it's a 0, it's a positive value. But 2's complement just takes the 2's complement of the whole bit of the whole word, and that's the way our computers store signed values too. Always is 2's complement. But this is straight binary here. So you sample at greater than twice the bandwidth. You choose the number of bits per sample you want to have, which gives you finer grained quantization error. There is quantization error that you can see from this picture that it quantizes it to one of the bit representations. And so from a comm system standpoint, though, we have this idea right here. So you get the right. No, that's not working. So the term that the book uses is 2NW, N is the number of bits per sample. W is the bandwidth of the signal, but we're going to do Nyquist low-pass sampling theorem, so we have to do Fs has to be 2 times W and then the number of bits. So that is our bits per second that we're going to send down our pipe. So as an example, if we were doing, let's just take our 8 kilobits per second that we've been playing with in the audio files that we've been demoing in class. Pick the right spot to throw this in. So if we were at, suppose our audio was at 4 kilobits per second, so we'd be at 4,000 hertz. We're going to double that because that's what those files represent, so times 2. And then telephony was using maybe 6 bits or 7 bits. So 4,800 bits per second, or if it was 7, 5,600. But then if they add another parity check bits in there, it might actually be 8. So telephony grade audio would nominally be around 64 kilobits per second. But if we were going to go with the original standards that we had for digital audio when the compact disc came out, it was 16 bits per sample. So that'd be 128 kilobits per second. And that's kind of what I'm using in my screencasting. In other words, when I post-process my capture today, I have to do the video compression with the MPEG-4, and then I also have settings that I make in my tool, Camtasia. How do I want the audio to go? I let it be mono, I don't have stereo audio, and then I have it running with 16-bit audio. So I'm doing 128 kilobits per second of digital audio is with the MP4 video file. But in the days of standard compact disc, we think about having 44 kilobits per second, or 44 kilobits per second. So there we're transmitting 1.408 megabits per second just for one channel. And this is in the notes here in a second, but since I'm just doing simple math, if you do left and right stereo audio, we're at 2.816 megabits per second. That's the width of our pipe, and that's, if you were storing this on your computer, that's what would be happening. So let's just jump back over to the notes now, and then we'll go through this example here. So we might use binary phase shift keying to just send the bits serially. We might use might use amplitude shift keying. There's a lot of different digital modulation schemes that can kind of manage more bits per second more efficiently. Binary is just 1-to-1. If it's 2.8 megabits per second, that's what is going to be on the BPSK carrier, and it's going to take up at least that bandwidth, if not more, in terms of megahertz. So the quantization error goes down, so the perception and the audio quality goes up, but it increases the transmission bandwidth. So the example I was just going through of 16 bits per sample is looking to have the noise power in the quantizer quantization operation guarantee you about 95 dB or better of dynamic range. If you're not able to set your if you have very quiet passages, though, they will not come through with that effective signal-to-noise ratio because they will be hovering around a small number of bits of resolution, so they'll have perceptibly more quantization error. Now, has anybody ever heard that before on a passage? If you turn the volume way up, it'll get noisier sounding. So we'll be able to emulate that if we want to here in a second. Compact disc digital audio, I forgot the point 1, 44.1 was the standard in 1976. It's PCM, left and right, And this is the format of the way PCM worked in the original compact disc format, which is the same today because it is a legacy standard. We have 9600 or 96 data bits. We have parity bits, and then we have a subcode and sync bits, 27 sync bits. So the sync bit idea is what I'm going to have you play around with in problem 2 of the project. But in this case, it's 1.4112, and there is a coding in this, and there's parity bits too to help protect against what? I mean, you're not so young that you have never touched a compact disc, right? Or a DVD or something. What can happen when you touch it? You what? Fingerprint, right? So the optical encoder is going to shine at the pits that have been put on the disc as a result of the recording process, and it may occasionally flip the bits. So some of the bits will have errors. So the standard allows for bit correction, forward error correction coding, due to dust, fingerprints, other things. I don't know. In my lifetime using compact discs, they can be pretty robust, but they do die on you. They don't die in a subtle way. They kind of just go bad. I mean, they will be so messed up that the CD player can't synchronize and get the music back again, or the video doesn't come back again. So how do we do that in the notebook over here? I have a pair of functions that are in the digital COM library. So that's, you go up here and just remember that we can import. Once you've done this a number of times in your Jupyter Notebook, it has remembered that, hey, you've been importing from Scikit DSP COM, then you hit Tab, and then it's the digital COM module that you want, and I generally import it as DC as my shorthand notation. I'm pretty sure it's at the top of this notebook already. It was imported, but that's what we have to do. So now we have these two functions, PCM encode, which takes your analog signal and it assumes it's bounded between plus and minus 1 in amplitude, and then you get to specify how many bits of PCM encoding you want to put out, and it will output a 0-1 bit stream. The decode function does the opposite. You give it the bit stream, the bits, and then you tell it how many bits it's decoding to. Now, the very nature of this, it assumes that the MSB and LSB are aligned so that when you send a digital stream in, it's right at the edge between one sample and the next sample of however many bits it is. So here I'm going to put some noise in to corrupt it, but I'm going to set it at, it's at 50 dB signal to noise ratio right now, and I'm putting in 4 bits in this example. And I'm only putting in 4 bits, just not because I want to listen to it, but just because I want to show you that it's got a lot of quantization error, and nobody would go with 4 bits. So if I just simply take this up to, say, 8 bits, which is 256, it's looking pretty good. If I was to subtract these two, I would see that there is quantization error in here. But what happens if I do some bit flipping in here? So I'll drop this down to around 10. Okay, I don't see any bit errors in there yet, but let's drop it down to 5. So what's happening with bit errors in the serial bit stream, if I hit on a more significant bit in the word of 8 bits long, I'm going to make more of an amplitude error. If I hit maybe only on the least significant bit, I'll get a little tick like that. So what comes to your mind when you see this, when you see these bit errors? What should be done? If we want to be robust, we need to do some sort of error correction coding in this, and what bits need to be more protected. the LSBs, the least significant bits, or the MSBs. And this is what's done in cellular telephony too. It's not PCM, it's another synthetic speech system, but it still has more significant bits. And so they protect the more significant bits with extra redundancy to make sure they can get back again. So they're willing to let through the less significant bits without any protection just because they want to keep it efficient from a total bandwidth occupancy point of view. So let's just do our UK speech guy and see if this will work. If it doesn't work, well, I'm going to put in 20 bits, take it back, take it through the length. These are some functions that are available in, well, I'm just writing this directly. I'm just summing up the bit errors because I know the bits should be I know what the input bits are, I know what the output bits are. So I'm taking out the encoded values in the input bits, and I can count the number of bit errors. And this is the measure of performance in a digital comm link. We're putting through 800,000 total bits, we get 0 bit errors. But if I drop this down to say 5, I'm now getting 4,782, so my probability of a bit error is actually quite high, 5.98 times 10 to the minus 3. With forward error correction coding, which we won't get into in this class, but you could drop that down by several orders of magnitude if you wanted to recover, we would put redundant bits in to be able to correct for errors, but we would be able to drop it way down. So let's just take a listen to this at 50. And this may not work without me resorting to my file.
The little tales they tell are false. The door was barred, locked, and bolted as well. Right here.
Okay, we've heard this before, so you know what it sounds like good. So let's just drop it down to 10.
The little tales they tell are false. The door was barred, locked, and bolted as well.
Did you hear that?
Right pairs
Little
are fit
speckle.
for a queen's table.
That's the sound of the errors. If I start to take this down now, I'll take it down to 8. It'll get kind of annoying sounding if I take it down really low.
The little tales they tell are false. The door was barred, locked, and bolted as well. Right pairs are fit for a...
Maybe it's not too thrilling, but it's definitely real, and this, is reflecting the type of thing that you'd expect to get. This is just looking at the input and the output audio. There's not anything, I guess there's an error right here. There's a few big errors. There's probably some smaller errors spread around in here, but if I was to drop this down, they would get up, but if I take this back up again and look at my analog output, like I just did, they're lying on top of each other, there's no bit errors. So, but if I do one little thing, and this is something that'll come up in the project, and you may start looking at this over the break or something. Let's just do something kind of silly. Let's go into our output here, and we have 8 bits per sample going in right now. So what I'm going to do is I'm going to slide this over to start at the 3rd location, and then I'm going to stride all the way up to -2 from the end. Or do I have to go -6 from the end? I think I have to go -6. So that way I'm taking out one 8-bit segment. I think this will work.
The little tales they tell...
No, I didn't do it right. thought I was going to get it off far enough where it was going to make a massive number of errors. It is making a lot of errors, but it didn't sound bad. What did I not do right? Because what I'm doing here is the decoder is expecting it's starting at the first of a frame of 8 bits, and I'm starting at 2 over, and then I'm ending at 6 over, 6 from the end, so that I removed a total of 8 bits. And it should have done worse than that. Bit error probability doesn't change because it doesn't know that I'm making bit errors. It's just the decoding operation is just not going to line up right.
The little tails they tell.
Okay. It's pretty, doesn't sound very good. And it's going to be louder, and the amplitude's kind of messed up. So, but that's what the synchronization will be. So you can see it's very much different. It's very hashy sounding because the bits aren't mapping properly. So we'll work on that. And the way what I'm going to have you do is you're going to embed a synchronization word, and then you're going to detect for that with correlation. You're going to do a cross correlation and find out where that sync word is, and then you'll know how to time the decoding operation. So what's next in the notes? The next thing in the notes, and this we're just about heading to the very end of the chapter, is a discussion of multiplexing. And there's 2 different types of multiplexing that are common. There's more than 2 types in comm systems in general, but we'll be looking at one type at the end of this chapter, and that's time division multiplexing, and then we'll look at frequency division multiplexing at the end of chapter 4, and then there's another type that's in common usage called code division multiplexing, and that's the way GPS works. Generation 2 of cellular did CDMA, code division multiple access, and systems I'm working on. I'm working on a project called LunaNet, I've said, and it's a GPS system for around the moon, and it uses multiple access with different spreading codes too. But the original types of multiplexing were time and frequency. So TDM is where you can multiplex more than one signal together, and you assume that we're sampling all the sources at the Nyquist rate, so we're properly sampling them, and then we combine them. And there's 2 different types of time division multiplexing. One is this kind of hokey looking thing, and this was what the this is what the sound tubes in an aircraft use. They would synchronize through a commutator just analog samples, and the channel in the aircraft sound tube case is the sound tubes themselves. But so the analog samples would pass straight through. That's analog time division multiplexing. But when you go with digital time division multiplexing, I don't think I have I don't have an exact picture. I don't have any picture in here at all. You just think of a digital multiplexer. You're just going to take, a bit from this channel, mix it in, multiplex them all together into a serial stream. Whereas this is kind of some formulas that the book put together that talks about the analog multiplexing scheme, the fact that you're going to have NS channels or NS samples over N channels in T seconds, and you come up with this formula. If I give a problem on this as a homework problem at some point, I'll make sure we talk more about it. But this is some of the notation that goes along with how to set up this scheme right here in order to make the bandwidths. And what a homework problem might be is it might be you have 2 sources that need 4 kilosamples per second, one that needs 16 kilosamples per second. So this one gets mixed in the commutator more frequently, whereas if they're all equal, then they're just, the samples are coming out in an order. That's an analog view of it, but in a digital multiplexer it would be the same way, right? If you brought in two 4 kilobit per second streams and then had a 16 kilobit per second stream, what's the total number of bits that you have to have? 2 of the 4s would be 8, and then the 16 would be, what is that? 16 plus 8 would be 34? 24, yeah, 24 kilobits per second, and you would be sending the higher rate one twice as often, and how the multiplexer is set up is, your choice, how you would do it, how you would pack the bits together. This one is set up, this idea is set up to be uniformly distributed, so that way when you decommute, you have the samples flowing roughly in order so they can go through just an analog reconstruction filter. In the digital scheme, it's how you want to packetize and depacketize the streams. What the telephone company did way back when it got into digital time division multiplexing, or TDM, and they came up with a hierarchy called North American TDM, and it was all based on a single voice sampled at 8,000 samples per second, 7-bit quantizer, 1 signaling bit, and remember I said before, break or whatever, whenever I did that, 64 kilobits per second. So then the telephone company still uses this standard today, where they talk about a single line and then they create this hierarchy. So how many voice channels do you get if each voice channel is 64 kilobits per second? So you have things like a T1 line would be 24 voice channels, which would be 1.544. And it used to be that if you were buying an internet service over the telephone company, just like you can do today still, you would say, I'm going to have a T1 or I'm going to have a T3 or whatever. I mean, the campus used to have so many of these types of interfaces just for our connection to the internet, and it's still done with this kind of a hierarchy. I think in a lot of cases this has been adopted, but I'm not an expert on it because I haven't really kept up with it to know. Does anybody know, or is anybody, it used to be you would say, I have a T1 line or I have a T3 line at work or whatever, but now you deal that out with Comcast, or not really Comcast, you deal it out, well, you can use Comcast, but you can use Ting Networks, remember I talked about that, or the other direct fiber providers that are available to bring a business a certain level of hierarchy. And now, rather than thinking in terms of voice signals, it's just thought of in terms of digital data for internet connectivity. But this grew out of the idea that you would have a neighborhood send in wire pairs, and then those would get multiplexed together with another part of your neighborhood, and then finally the higher bandwidth hierarchy would backbone connect it to the switching center for your telephone connection. But I don't know, where do you guys stand? My wife and I each have a cell phone. We don't have a wireline phone into our house. Out of curiosity, how many of you still use a wireline phone? I mean, your parents or your family?
Not even them anymore.
Okay. Okay. See, we all said, why do we need that? My house has the telephone jacks in it, and we've been cleaning up the house. Like I said, all these hours I've spent backbreaking work, hauling junk around, literally. But I'm looking at how they worked in the basement, and they peeled off all the wall plates and things. The fiber, or the cable that we have for our cable that was put in when the house was built 40 years ago is still there. But then, and I'm saying that could still be useful, but then places where there were wall jacks for telephone, what do I care about that anymore? I mean, I think they're going to leave them there, but I don't know if anybody will ever use that. It's wiring inside the house, but it's not in infrastructure that I use anymore. We had it disconnected and canceled our subscription to the telephone company. It seems strange. Being I'm a comm systems person, we went from primitive telegraph and things like that. We had twisted pairs for voice, and now we mostly care about data. I mean, that's what my family mostly cares about. And there's 3 of us in my household because my one son still lives at home, and everybody uses data. They don't think about anything but data, and this was the beginning of it. So what we will get into after break will be, get this thing in the right position here. We will switch gears, and we're going to be in angle modulation, and just come back. This is a good closing point. The top there, we're not going to have, AC is going to be constant. So when we're in angle modulation, we don't let that vary in proportion to the message, whether it be analog or digital. We just hold it constant, and all the information is going to be in phi of t, the phase. It could be in terms of frequency, which would be frequency shift keying for digital, or analog FM would be frequency deviation, or it could be in the phase. And in the lab, you'll be working with FM. When you start in lab 4, you'll be working with FM modulation in the radios. You will be able to work with those radio boards without knowing about FM demodulation initially. You're just going to know that it exists, and the board has that capability on it. But we'll get into this, obviously, after the break. I wish everybody well. I'm going to sign off right now.